Hello student, welcome to the class. Today we will be working on the basics of matrix and some matrix operations. Let me begin. The first question is about the definition of matrix. Which of the following best defines a matrix? A rectangular array of numbers arranged in rows and columns, a single number representing a scalar, a sequence of numbers arranged in a line, a graphical representation of data points. um, you must be clear, having after watching the video on matrices and matrix operations that a matrix is a rectangular block of numbers. Okay. The horizontal lines are the horizontal array of numbers are rows and the vertical ones are columns. So which brings us to the special types of matrices. Okay. A general matrix is a rectangular matrix. The special cases are which of the following is a row matrix? A row matrix, as the name suggests, will have only one row in it. So it's called a row matrix. Okay. In that context, we can say the first one here is a column matrix. It has only one column. Whereas the third option here is a square matrix. It has equal number of rows and columns. Okay. The fourth one is the general rectangular matrix, not any of the special types. Next, a matrix with dimensions 4 by 1. Understand that. Okay. So that is also a conceptual clarity on what is dimensions. When you write dimensions, we always write rows by columns. Okay. Dimensions is always rows by columns. So if it is 4 by 1, that is 4 rows and 1 column. So clearly that's a column. Okay. Which of the following is a square matrix? And I think now it's clear. We already saw that example. If a matrix has 3 rows and 5 columns, what kind of matrix it is? Okay. Now this does not have equal number, right? Different number of rows and columns. So it is just a regular rectangular matrix. And which of the following is both a row and column matrix? That's an interesting one, right? And if you think about it, there can only be one dimension that fits that definition. Okay, which is this. Because if the moment you have two columns, it cannot be a column matrix. If you have two rows, it cannot be a row matrix. So one row, one column, that is 1 by 1 matrix. Okay. Right. Moving on. Addition and subtraction of matrices. Okay, now we are getting started with operations on matrices. Given matrices, these two, find the sum A plus B. These are practice problem sessions. You should, okay, always pause, try to solve on your own, and then check with me. And the solution is the matrix addition is defined by component wise or element wise. Okay. Here, this is component wise, or in other words, we say corresponding elements. Wise means like you add the corresponding elements or add the corresponding components. Okay. which is the first row, first column, they are corresponding. So 3 and 1 will be added. 3 plus 1, 4. 5 and 0 will be added. 5 plus 0, 5, and so on. Okay, I will now continue. 7 plus 2, 9. 2 plus 3, 5. 4 plus 5, 9. 6 plus 1, 7. Okay. Similarly, subtraction works the same way. Okay, you look at corresponding elements and you do the subtraction. So C minus D in this case will be 4 minus 2, 2, minus 1, minus 3 will be minus 4, 3 minus 3, 0, 2 minus 0, 2, 0 minus 1, minus 1, 5, minus minus 2 makes it 7, 7 minus 4, 3, 1 minus 6, minus 5. Okay. At this point, I have to say you can only do if the dimensions are equal. Okay. When are they compatible? In both these examples, of course, they are compatible. They have the same dimensions, so you could do. But for example, in the case of, the question number 7, if the matrix B was like just 1, 0, and 3, 5, suppose I'm saying, okay, suppose, then you cannot add A and B. It's not like you can add only the first, 4 components and the last column. You can just leave it as it is. It's not like that. Okay. So if this was the case, we would say not compatible for addition or subtraction. Okay. Similarly here, this is a practice problem for you. And question number 10 is another practice problem. I'm going to pause the video and display the solutions. You do the same and check your answers. Okay, check your answers now. The interesting thing about the results we got here is in question 9, the matrix you have, you can pull that 7 out of the matrix, which is a scalar multiplication operation. Okay, that, if an entire matrix is multiplied by a number, then that number multiplies every entry or every number inside the matrix. So for example, if I were to multiply by 7 a matrix which has 1 1 1 1 1 1 like that, it will result in that 7 7 7 matrix. Okay. And by the way, we don't discuss much in this course about this matrix, but this all ones matrix is also an interesting matrix for study. Okay, if you do some higher mathematics in the future, you will sometimes be dealing with that. Okay, we talk about all zeros, the zero matrix or the identity matrix which has ones in the diagonal. This is also another interesting matrix. Okay, and in the next question, I hope you were careful that you should be subtracting g from h. Okay, so it's h minus g, not g minus h. Okay, moving on. Now we are getting into the matrix multiplication. We begin with the idea of multiplying the simple one first, right? Just one row with one column. Okay. So question 11, multiply that row by to that column. Okay. And as you must be aware, the only multiplication you can do here is r times c. Or can we do the other way also? R times C works. Does C times R work? That will be 3 by 1. Yeah, sorry. So both of them will work. Okay, and I think it will be fun. We will do both of them. RC will be the row times column, right? That is how matrix multiplication is defined. So 2 times 4, okay, plus negative 1 times 0 plus 3 times negative 2. As you move across the row, you move down the column and you multiply the elements in the corresponding positions, okay, and take their sum. And all of that goes into one element. That becomes one element in the resulting matrix. And as you can see here, this gets like 8 plus 0 minus 6, so 2. When you simplify, so it just becomes 1 by 1 matrix. And why is that? Because the row matrix was a 1 by 3 matrix and the column matrix was a 3 by 1 matrix. And as it happens in matrix multiplications, these numbers will vanish and the first and the last, 1 by 1 is the product that you see here. And I was saying, because we are doing practice problems, why not do the other way? And that also highlights the fact that matrix product is not commutative, as we talked about in the lecture video also. It's worth repeating important statements, okay? Matrix product is not commutative. Okay, so you cannot, if RC and CR will not be equal, as you will see now. Okay, how? When you multiply CR, you will be writing the column here first, and they will be writing the row. Now what happens? You multiply, the logic is you take the row and multiply with the column, and that becomes your entry in the resulting matrix. 4 times 2, 8. Then you move to the next column. 4 times negative 3. Or you could do row wise or column wise, okay, depending on your choice. I'm going to fix the row. I'll stay with 2, okay. Let me use a different highlighter. I'll stay with 4 here, sorry, not 2, and move the columns in the second matrix. So in the product also you move the columns. So 4 times 2 is 8. 4 times negative 1 is negative 4. 4 times 3 is 12. Okay. And the concept of matrix multiplication is the row number comes from the first matrix, right? This is row 1. Okay. And these are column 1, column 2, column 3, right? C1, C2, C3 in the second matrix. And that's what happens here. This is like, A sub 1, 1, first row, first column, A sub 1, 2, first row, second column, and here it is A sub 1, 3, first row, third column. Okay. Then we are done with that row with in multiplied to every column. You move to the next row and multiply to every column. And as you multiply with 0, 0 times 2, 0, 0 times negative 1, 0, 0 times 3, 0. And negative 2 times 2, negative 4, negative 2 times negative 1, 2, negative 2 times 3, negative 6. Okay? And that would be a dimension wise, that would be a 3 by 3 matrix, as you should expect, because you multiply it 3 by 1 to 1 by 3, right? So the middle numbers will vanish. first and last 3 by 3 would be the product. Okay. So a lot of things here, we like reviewed when can you multiply matrices. The number of columns in the left matrix should be with the number of rows. Those numbers should match the ones in between. Only then you can multiply. They will be compatible for a product. And the RC and CR may not be equal. Okay. Calculate the product of row matrix and the column matrix. The next one is for your practice. Um, just like the previous one, I will do both. You do the both and check your answers with me. You can check your work now. Move on. Matrix multiplication. Okay, now we're doing a matrix multiplication of more than one row and one column. Okay, let us multiply A and B. So again, the multiplication works because A is 2 by 3 and B is 3 by 2. It's always good to check that. Okay. Not only that, it will tell you if they are compatible, which they are here, but you will also know the dimension of the product. So your product AB has to be 2 by 2. If you make sure you do that, right, even before you do the matrix product, if you know the dimensions of it, hence you are likely to get it right. Okay. Now the same logic, first row with first column gives you the first row, first column element in the product. So 1 times 2, I'll do that work on the side here. Okay. So 1 times 7 plus 2 times 9 plus 3 times 11. That will be 58. Okay. Goes here. And now I will go to the second column. If I go down to the second column, it will be 1 times 8 plus 2 times 10 plus 3 times 12. Okay. So that is 8 plus 20, 22 plus 36, 38, again 58. Is that right? Interesting. That comes here. Okay. Similarly, you multiply, the second row with first column, and that becomes your second row, first column entry. Okay. Which we will do here. 4 times 7 plus 5 times 9 plus 6 times 11. And that will be 28 plus 66 will be 86, 94, and 45 will be 134, 139. Okay. You can double check your work with me. And finally, 4 times 8 plus 5 times 10 plus 6 times 12. Okay. And that will be 32 plus 50, 82, 82 plus 72, 154. Yeah. Okay. Now, in this case, you could also do B times A, which I'm skipping for now, I think, because we'll be doing one more next anyways. B times A, you can do it, okay, if you want to, do more practice. B times A, if you do, you will get a 3 by 3 matrix. Okay, calculate the product of C and D. It doesn't say CD or DC. Shall we figure that out? Okay. If you look at C, that is 3 by 3 and D is 3 by 2. Okay. So there is only one way you can multiply, right? Another interesting fact here. So CD, if you multiply, these two will go away. So you'll get a 3 by 2 matrix like D. Okay. But DC, if you try to multiply, it will be 3 by 2 and times 3 by 3. Now that does not exist. Okay. D and C, that way they are not compatible. Right? So another important thing to remember, it's possible that you can multiply one way, but not the other way in matrix multiplication. Okay, so let's compute CD. You can do this and then check your answer with me. Okay, I will pause and show you the answer. That is your product CD. Let's check your answer and then do the similar work with EF, where we can see E and F there. You can multiply and check your work. And also after that, um, multiply G by H, it says. Okay, the question number 16. In that we will do HG. Okay, EF here and HG there. Two more problems for your practice. Please do it and check with me. Check your work now, and especially the HG matrix. Is it not very interesting? Observe how these rows of the type 1 0 and 0 1s, don't essentially change the numbers. They just, keep the first row or the second row of the next matrix. Okay. In fact, you observe that if you just look at the first two rows, that is the identity matrix, right? Of the order 2. And it is actually maintaining the same matrix. The product that you get here is the same as the matrix H, which you have here. And then after that, the next block is another identity matrix, and you get the copy here, right? This is a very interesting, property of matrix multiplication with rows that only contains ones and zeros. And later, again, if you do advanced mathematics, you will learn something called permutation matrices, which only contains these ones and zeros. In every row, there will be one, and rest will be zeros, but in different positions, not just the identity like diagonal. If you randomly have ones and rest of them zeros in every row, it is what is called a permutation matrix. And the effect of that matrix will be it will move around numbers of the other matrix, like the one that you see here. In this case, it keeps them in the same position. If you change the position of one, it will just rotate the numbers in different positions. But overall, the matrix elements will be the same, simply permuted, what is called permutation. Okay, shifted their positions, right? Interchanged or rearranged. It's like jumbling a word. You can think of some applications, right? If you want to create a code by jumbling the letters, we might use matrices. Okay, matrices are fun. Okay, some knowledge question here again. Which of the following is an identity matrix? As we were discussing just now. I hope like it's not difficult for you to first see that the answer is this, but we will discuss more. Okay, and that's an identity matrix because it has the diagonal entries are 1 1 1 and the rest of them are zeros. Here, that's not identity. Sometimes you might be confused. Okay, not. All right. And this one has a problem. There is an extra one. You cannot just have the ones on the diagonal. That is not enough. In fact, the one in the item B here is a kind of permutation matrix. You should try to multiply, any 2 by something matrix with that and see what happens. You'll see that, first row will become second row and second row will become first row. It will interchange the rows. It is an interesting matrix. Over here, D, almost identity, but the problem is these are called what you can say it's a diagonal matrix. Okay, diagonal matrix, and you can say scalar matrix. Diagonal scalar matrix. What that means is you could take the 2 out of it, then what remains would be the identity matrix. It's a multiple of an identity matrix. Okay, all right. Um, Next problem is converting the linear system and solving by inverse matrix method. Now, the original plan of this question was to just convert it into the matrix form, which is what you needed to practice. But also I added the part where you will find the inverse matrix of A. And if you are watching this sequence of videos, for this course, you might wonder that we have not yet learned the technique of finding the inverse of A, right? That is correct, which is our next lecture. And what I will do now is we will just write the matrix AX equals B for all of these questions where that is required. And finding inverse or solving by inverse, we will do as practice when we come back to the next lecture. Okay, so in the next set of problems, I will also be doing a separate set of problems, but also come back to this file and do the inverses. You also do that. Okay. After you watch the next lecture, come back and do the inverses before you watch my next video on problem solving. Okay. Now, what is the question here? The question is, there is a system of matrix equations given and you convert that into a matrix form. And how do you convert it to a matrix form? You take the coefficients and convert that into the coefficient matrix A. Now, A is going to be the coefficients. Okay, X is going to be the variables X, Y, and Z, and the B is the constants on the right hand side. Each matrix there has its own purpose. Okay, let us write that. So this would be the matrix A will be coefficient. So 2, 3, minus 1 for X, Y, and Z. From the second row, 1, 4, 2, third row, 3, negative 1, 1. Right? And then X is the variables. Just doing the exercises is like simple, okay? I know, I'm sure you just immediately do it. But I wanted to talk about, that coefficients, variables, and constants logic of the whole thing, okay? And it comes from matrix multiplication, by the way. Now, if you take this matrix, and multiply with that column X, Y, Z, you will get, you will recover that equation, right? 2x plus 3y. If you move down here, 2x plus 3y minus z will be your first entry. That is the first equation there. And on the right side, you write the constants. So equals 5, equals 6, equals 4, the three equations. Okay, that is the matrix form of the given linear system. Okay, we will find the inverse later. And once you find the inverse, you will be doing this question number 19, where you have the inverse. Once you find the inverse, you multiply the inverse with this b here on the right side, and that would be your solution for x, y, and z. Okay, all right. Here is another question. It asks you to convert that system into matrix form and then solve. This is a 4 by 4 matrix system, 4 variables, right? For you to practice. So please write your solutions and check with me. Check your work and remember to come back and do the inverse of this 4 by 4 matrix, which will be real fun, okay, after the next video. Okay, now we are moving to some application problems in matrices. Okay, each question is very interesting, real world application of what you have studied, will be very useful for you. Read the question carefully, try to be ahead of me and solve, and then watch my video. Then you play the video. Um, at least for the first question here, I think the other two questions are going to be relatively straightforward if you give a little bit of thought. This question you might want to, there might be different approaches. You think about one approach and then play my video and see what I do. Okay. And here's what I am going to do. I will just call the given table as a matrix 150, 200, 100, 180, 220, 120, 210, 250, 130. Okay. And this matrix which takes me back to the definition of matrix, right? What we said, it is a rectangular array of numbers, but what meanings you give to those numbers is up to a particular situation. That's what I had said in that video. And here is an example. Now, the rows of this matrix correspond to the years 2019, 2020, and 2021. So we do not write them in the matrix itself, but that is our interpretation of the row. Okay, that's like a metadata, extra data about the table. Okay, it's like row header. In an Excel sheet, you in the first top row you have the headers like name, student email, student what you call ID, and then like your measure and so on. Like if I look at your roster, like that, these are headers. Okay, for the rows. And columns also have meanings. Now matrix, it has both of them have meaning. Okay, the columns like these ones are for the sailboats. The second one is for motorboats. That is the number of cells, right? In those 3 years. And the third one is for kayaks, right? Okay. Now it says write a matrix formula to find the total sales in each category. So which means basically we are talking about what is the total sales of sales boats and so on. And you can obviously see, basically we're adding the columns. As a matrix formula, how would you write it? What I will do is, I'll create a new matrix, call it T, which is total sales. And in the total sales, it will be like a single row matrix now. Okay. And the entries of that row, the first entry, and if you're doing this actually for many years, let's say not just 3 years, I'll talk about in that perspective also. Suppose, in another question, you are doing 10 years total sales, then you might want to use this notation. This is the sum notation, right? Sum of what? From the matrix A, in terms of the matrix A, okay? A, I, 1. 1 here, the 1 is the first column. Okay, I will be the row number and that will change, right? First row, second row, third row, but all of them in the first column. So that sum AI1 will indicate or represent the sum of elements in the first column. Second one would be sum of AI2. Okay, sum of elements in the second column. And similarly, the last one would be sum of AI3. Okay, so you could use a notation like that in general. In this case, it's very easy, just three of them. You add them and you write your answers here. Can do that and check with me. Okay, those will be the total sales in each category. The next question, very interesting word problem again. Okay, profit and uh, production costs and profits at Gauss Jordan sneakers. Okay, that is a fun name. We studied the Gauss Jordan elimination method. Okay, we're simply having fun here. Jordan speakers, not Jordan, Gauss Jordan speakers. Okay, sneakers. And so, what is given to you? You are given costs and profits. Okay, um, that might represent costs in different categories. Okay, that part is not explained in the question, so we will understand that. Okay, um, at different sectors, it looks like if you look at the last part of the question. Okay, maybe there are four sectors, so the costs and profits from those four sectors in a year, right? Okay, now what you need to do is you need to write a matrix algebraic formula to compute the revenues. Okay, and that is the real world part where our knowledge is the profit. It's easy to first remember that way. The profit from a business is what? The revenue that you earn by selling minus the cost that you incurred in manufacturing and the whole operation, okay, and selling. So profit is revenue minus cost, which means if you want to compute the revenues, now I'll use shortcut. Revenue will be cost plus profit, right? Take it to the other side and add it. And the matrices you have here are cost and profit matrices. So your revenue matrices, okay, will be the sum of them. So the 5,000 and 2,000, 7,000, 7,000 and 3,000, 10,000, 6,000 and 2,500, 8,500, 8,000 and 3,500, 11,500. Okay, think about that. Very interesting. Next problem. Again, very interesting. Okay, so there is a bookstore. Left Coast Bookstore has two stores, one in San Francisco and one in Los Angeles, and it has three types of books, right? Hardcover, softcover, and plastic for infants. Okay, kids play books, with all the diagrams, cows and pigs and birds and all that. The table shows the number of books in stock at the beginning of January, this one. And as will be explained on the next page, the rows and columns have meanings, right? The first row is for San Francisco and the second one is for Los Angeles. Okay, the inventory, of what the columns also have meanings: hardcover, soft cover, and plastic. Okay, the same in other matrices also. Okay, that order is explained here, and that is on this page what you had was inventory. Okay, that is the inventory you had at the beginning of the January, and in January this was the amount of sales. Okay, again, San Francisco and LA, hardcover, softcover, and plastic. And the s- stores also do restocking, right? You have inventory, you do sales, and you will be doing restocking simultaneously. And these are the restockings for the um, month in that month. Okay. Now the question you are asked is use operations to determine inventory at the end of June. Okay. Is that should have been January? Yeah, there was a typo there. Okay, at the end of January. Okay, think. What I would say is this: think how you do compute that, and then check your work with me. Okay, and my answer is this. Okay, inventory at the January end. Okay, will be now I have to use shortcuts. Inventory at the Jan beginning. Okay, minus sales plus restockings. Right? So the three matrices you are going to um, add and subtract in this way. Do that and check your work with me. Check that. Okay. Um, so looks like they are overstocking the hardcover and soft cover. They restocked more than they sold. Probably down in business. Only the children's book they were able to sell more than they restocked. I think they should change the strategy next month, right? They should get more children's book and less of hardcover and softcover, probably adult books. Okay. Uh, Next question. Again, very interesting. What does it say? The table gives number of people in thousands who visited Australia and South Africa in the previous year. Okay. Now, from where? The columns are here, Australia and South Africa. Okay, the two countries, and the rows are the different regions from where they came. Okay, the tourists. That is North America, Europe, and Asia. Okay, and there is a prediction now. What is the prediction? There are these four rows which make the prediction. Okay, 20,000 fewer people from North America will visit, and 30,000 more will visit South Africa. Okay, uh, so that is, I think this 30,000 um, is they're talking about from North America. So from North America, 20,000 less to Australia, but 30,000 more to South Africa in the next 10 years. Similarly, 80,000 more from Europe will visit Australia and South Africa both, and so on. These kind of predictions are made. Okay. Use that information now to do a matrix algebra and predict the number of visitors 10 years later. Okay. So how would you incorporate this predictions data into that matrix? Think of that. Okay. How would you do this using matrix operation? What kind of matrix operations you are only given one matrix. So how would you go about processing this rest of the data? Again, pause, think, and then listen to me. Okay. So my proposed solution is this. You create this new matrix. I call it delta visitors. That is the delta symbol. Okay. Which means change, right? Change in the number of visitors matrix. You know, you have a number of visitors matrix and take the change in number of visitors matrix. And both matrix will have the same headers and columns, right? So this change in visitors matrix will reflect the change in the numbers that will happen over the next 10 years from each region to both Australia and South Africa. So for example, when the first uh, row prediction here, okay, the first prediction here when it says there will be 20,000 fewer visitors from North America to Australia, that will go here. North America to Australia, 20,000 less. Okay. And 30,000 more to South Africa. There. Okay. And so on. Fill in the data similarly from the other predictions. For example, it says 80,000 more from Europe will visit both Australia and South Africa. So that will be 80,000 for Australia, 80,000 for South Africa. So the positive entry here means they are more, visiting. Negative means fewer people, less people visiting, right? 150,000 from Asia will visit South Africa. Sorry, that should go here. 150,000 here. Okay. No change in number visiting Australia. I mean, this same thing. I should have put it in the same row. So from Asia, no change to Australia. That will be, that entry is 0. Okay. Now you have your visitors and number of visitors matrix. The number of visitors from 3 regions 10 years later, that will be your new matrix, right? Visitors 10. Let's give a new name to that matrix. 10. So that will be the number of visitors, 10 years later would be your current visitors matrix plus the change in the number of visitors matrix, right? So when you add these two matrices, it will reflect from the current what will happen in the future. Okay, and please do that operation from those two matrices. You can see them here and then check your answer with me. Okay, if you are confused while solving, I didn't mention one thing earlier. This one is in thousands. Okay, so the first table gives the values in thousands. So that means when you say 1000 here, that is 1000 thousands. Okay, that's a million people. All right. Otherwise, you might be getting some negative numbers here and wondering what's going on. Okay. So those values are in thousands. So when you do this matrix addition, um, do the, interpret the first number here as 1,000,000. Okay. And also I'm going to make a small edit here. I'm changing the question. Sorry again. But the numbers are simply too big to compare. Okay. So what I will do is I'll just strike off zeros from the end of the matrix. Okay. So like 100,000, I think a million is too much. Okay. So 100,000 and similarly 80,000 in the first column here. Okay. When you read here. So 120,000, 90,000, 150,000 here. Okay. And 110,000. So just let's remove the zeros from the end. So our matrices will have some meaningful data. Okay. So I wrote my answers like that. What I did was I converted this number of visitors matrix to in thousands units. Okay. Previously I had written 20,000, I changed. So if you take the scale of 1000, so that will be -20, -30. Now both matrices are in thousands. Okay. Then you can do the operation easily. So for example, the first entry would be 100 minus 20, that is 80 here. Okay. And so on, you can do the matrix addition like that and get your results there. Now, what that means is these many thousands. Okay, there will be 150,000 visitors from where Asia to Australia in 10 years, and so on. Okay, with that, we are at the end of this problem solving session on matrices, operations on matrices. Another important operation, that is to find the inverse of a matrix, because it's an important and a separate topic, to be studied in itself. I have made a next video for that. And then, as I said, don't forget to come back and solve the equations in this file as well as in the other file. Okay. Thank you. See you in the next lecture.